When I was 12, I wanted to be Iron Man. Unfortunately, I grew up in Kansas. And if you've ever been to Kansas, you'll know there's only 3 things to do: farming, football, and funny jokes. Luckily, my family had a computer, which meant that I could escape through the power of the internet. The first thing I did was Google how to become an electrical engineer. And now, 10 years later, bada bing, bada boom, I'm an electrical engineer. Magic!
And by magic, he meant 10 years of suffering.
Actually, it sucked. The truth is, what I wanted to do was build cool things, and I didn't really need a degree to do that. When I was 12, what I really needed was a tool. I needed somebody to hand me a board, a platform, and say, this is how you're going to learn electrical engineering. So, I made it myself, and it's called the tinyCore. It's a custom PCB that teaches you how to design your own circuits and build your own products. And today, I'm going to explain to you how I made it. Designing PCBs is actually very easy. It's one of the best kept secrets in electrical engineering. Probably because the electrical engineers want to keep their jobs. But today we're going to be explaining exactly just how to make one. The first thing you need is software. It's called KiCad, Electronic Computer Aided Design. There's a lot of them. Altium, KiCad, Fusion 360, which used to be Eagle. I picked Altium. It's an industry standard. And yes, it is very expensive, but it's free for students. So that's a future me problem. After I picked the software, I opened up Altium and I made a new schematic. Let's talk about components. The goal of this project was to create a highly integrated PCB, and the ESP32 helps power that. It's got built-in USB support, which I used USB-C to break out. It also has Wi-Fi and Bluetooth, and it has a great 240 megahertz processor that you can actually run TinyML and AI algorithms on. I also added LiPo management, so you can charge and discharge batteries through the USB-C. And I added motion tracking, so you're able to measure movement in the X, Y, and Z axis. Lastly, I wanted storage, so I added an SD card that's available over SPI. If you want to know what any of these acronyms mean, we have a full write-up link in the description. Once I had all of the parts picked out, I downloaded their libraries and I put them into a schematic. And then I connect them with wires. Adafruit proved to be a very good resource for this, as many of their microcontrollers actually have open source circuit diagrams that you can use for copying subsystems. So the battery management on the board was used directly from Adafruit, as well as the wiring for the ESP32S3. The next step is creating the board. We need to decide a shape, and I chose an octagon. Because heck, octagons are cool. They're sexier than a square, and they'll fit a lot more niche applications than a rectangular PCB. You want to make a smartwatch? Try duct taping an Arduino Uno to your wrist. tinyCore makes that easy. Smart thermostats, round displays, circular robots. We can build it with an octagon. So now we have our board shape defined in Altium, and we need to focus on component placement. One of the biggest issues with this ESP32 dev boards is that their pins are mixed up everywhere. They're completely random numbers. 8 is next to 15 and 22 is next to 36. It makes no sense. Sometimes the boards don't even have labels on them. I wanted my board to be different. It's very simple. Analog on one side, digital on the other side, serial underneath. That's 3 sides. We still have 5 sides left. I freaking love octagons. Next, we need to place the microcontroller. This is the most important piece because it has a built-in antenna. No more plugging and unplugging antennas and risking them breaking. It's all integrated. This antenna needs its own space, and here's where we made our biggest trade-off. Most antennas are supposed to have nothing all around the antenna. And although we did do a PCB cutout by removing the copper underneath of the antenna, we did still have to place buttons next to the antenna. However, even though this isn't best design practice, after manufacturing and testing, we've found no meaningful difference in wireless capabilities. So we have all of our I/O set up, and we also have our microcontroller placed. Now, what I want to do is increase compatibility. I want people to be able to use this device with very few wires, plug and play. The easiest way to do that is to use something called a stemma or quick connector, which is an accessible standard for Adafruit and SparkFun libraries. It uses a 4-wire protocol called I2C, or I don't remember what it's called. Anyways, it uses a 4-wire protocol called I2C. This will make it easy to connect a huge array of sensors with nothing more than a cable. After that, we need to add the USB-C port and the battery plug. I'm gonna put the USB-C port down in the bottom right corner, and I'm gonna add the battery plug to the bottom left corner. We'll add the battery management circuitry right near the battery plug, And we'll add the USB-C circuitry right near its respective port. Now, let's see. We have 3 sides for I/O, 1 side for the antenna, 2 sides for quick, and 2 sides for the battery. That's 8 sides. We're out, but we still have an SD card. Where are we gonna put the SD card? That's when we have to start thinking in 3 dimensions. Remember, there's actually a backside. So I put the SD card on the back of the board, but we had to make sure it faced up. And the reason why we did that was because if we faced it down, it would hit the pins. So now we have almost everything placed on the PCB, except for the IMU, which stands for Inertial Measurement Unit. Lots of funny acronyms. That's for tracking our motion, and it needs to go right in the center. The reason it goes right in the center is because of something called tare. T-A-R-E, not T-E-A-R. Tare has to do with the fact that when you rotate an object, it rotates more on the outside than in the middle. The closer the IMU is towards the middle, the more accurate it's going to be. We've also added indicator lights, so you now know when the device is receiving power, when it's charging, and you have 2 custom lights that you can program for whatever you'd like. Next up is routing. After we've placed all the components, we need to start connecting them with wires. And this is what we've set up in the schematic. As you can see, all of the devices have these thin lines between them, and we have to decide how to connect them in the most optimal way. There's actually a game that I found as a kid that I had no idea was going to teach me how, but it's called Flow Free. And if you download it and practice on some of the harder levels, it'll teach you exactly how to run circuits. It's all about optimization. It's kind of a puzzle, and I actually find it to be one of the most cathartic parts of circuit design. After we've run all the routing, it's time to add a silkscreen. The silkscreen is a layer of usually white ink that labels all of the components and features of the board. On our board, we've labeled the analog, digital, and serial I/O, and we've added logos for both tinyCore and the Open Source Hardware Association. Of course, this logo is special. You need to get permission for this, so that means that our board meets rigorous OSHA standards. Lastly, we're going to add ESP32 boot instructions, because anybody who's used an ESP32 knows how much time you have to spend pulling your hair out to try and figure out how to get the device to work with your computer. Try finding that on any other ESP32 board. Let's go over what we've done so far. We've made a schematic, placed the components, wired those components together, and labeled them with a silkscreen. Now it's time for manufacturing. And this next part is actually very exciting. For this project, we were sponsored by PCBWay. PCBWay is a PCBA manufacturer. That means they create both the PCB and assemble the components on it. We had ours done turnkey, which means they provided all of the parts and mailed the boards directly to us. Once they arrived, we were ready for testing. Now we need to make sure the device works before we ship it to anyone. To do this, we're going to take a bunch of measurements. We're going to take voltage measurements of all of the pins, make sure all the power regulators are working, and make sure that the I/O works. We're also going to try flashing the board, make sure all of the LEDs are functioning, and make sure that a computer can recognize it. Lastly, we test out the LiPo battery and the SD card slot. If we pass all of these tests, the device is ready to ship. And ta-da! That's how you design a tinyCore. Now, a big part of this project that we haven't talked about is what you're watching right now. Everything in this project is open source, but it's not just open source. A lot of projects that claim to be open source and claim to teach you about electronics do not provide their engineering judgment. They will simply give you a downloadable file of CAD, which is very useful if you already know what you're doing, but it's not going to help you learn. The reason we're making this video is to promote open knowledge. We want you to be able to understand why we made the decisions we did, why we included the features we did, and some of the engineering trade-offs that we had to make. If you'd like to follow the progress of tinyCore, please subscribe to our YouTube channel, Mr. Industries. Also, join our Discord. We have office hours where we can help you with your tinyCore project. Thank you so much for watching this video. I hope that you learned something. This is Jeff, signing out. Click. And please subscribe if you want to see more.
Pee-pee and poo-poo. Sorry. Please.
You talked over me.
Because it wasn't a good take.
Aww. Now we've got almost everything placed on the board, except for the IMU, which stands for Inertial Measurement Unit. Inertial Measurement Unit. Duh. Hey. I don't like being the other person on the end of this. This is how I treat people. I don't like it.
Poor baby.
Yeah.
Do it.